Hello everyone, a very good evening to all. I welcome you all again for the interaction session on atomic and molecular physics, which is being flowed this January 2024 session by NPTEL with course code NOC 24 Physics 04. Myself, Vivekananda Naik, I am a PhD research scholar in the Department of Energy Science and Engineering, IIT Delhi. So today this is our ninth interaction session, and in this session we will be discussing about a few problems that will be based on week 9 lecture of the course. That will mainly cover the quantum mechanical treatment of hydrogen atom and hydrogen-like atom, and some of the sample problems related to the uh, molecular spectra like rotational and vibrational spectra. So let's start with the first question of the day. Now the question says, given the normalized wave function psi x equals to n uh, divided by x square plus a square, find out the normalization factor n when x is varying between minus infinity to plus infinity. The options are option A 2aq by pi, option B 4aq by pi, option C 6aq by pi, and option D 8aq by pi. All are square roots. So I will give you a few minutes to try this question. Then we will solve and find out what will be the correct answer of the, that is, what will be the normalization factor n for which the wave function, the given wave function will be normalized. So let's solve this question. Now the question is where the wave function is given. The wave function psi is given as n divided by x square plus a square. Now we have to find out the normalization factor, and the range of x is minus infinity to plus infinity. So according to the normalization condition of any wave function, because the wave function in order to be uh, acceptable, it should be always normalized, and that also signifies that the overall, we know wave function has no physical significance directly, but if you talk about the mod of the wave function, that is psi mod square, then it gives us the probability of finding the particle in that region. So if we integrate it over a region, suppose this is dx and there is limit from minus infinity to plus infinity, so it will give us the probability. And since the limits are from minus infinite to plus infinite. So this integration will always yield 1. That is, the particle is definitely present between these ranges, minus infinity to plus infinity. So basically, this equation is called as normalization condition. Normalization condition. And also this condition can be written otherwise as minus infinity to plus infinity psi star psi dx equals to 1. So we will perform the same integration using this given wave function. So if you put it, we will be having n mod square, because since the wave function, again the wave function is real, so psi x and its conjugate both will be equal. So in both the cases there will be n, so n mod square, then integration is from minus infinity to plus infinity. Psi is 1 by x square plus a square, so it will be 1 by x square plus a square whole square into dx equals to 1. Now talking about the integration, we know the integration for there is a formula for this particular type of integration. We know integration from minus infinity to plus infinity, 1 by x square plus a square is 1 by a tan inverse x by a, like this. So if you talk about the integrations, so you have to convert this integration to a different integration, so that we can use the below formula. So doing that, what we will do first? First, we will take the integration of minus infinity to plus infinity dx divided by x square plus a square, and it will be 1 by a tan inverse x by a limit minus infinity to plus infinity. So if you put the limits, then it will be tan inverse x by a, limits are minus infinity to plus infinity. So if you do it, it will be 1 by a, then tan inverse infinity minus tan inverse minus infinity. So this is tan inverse infinity minus tan inverse minus infinity. So it will be 1 by a. So it will be pi by 2. So tan infinity is tan pi by 2. So it is pi by 2, again minus of minus pi by 2. So it will be 1 by a into pi. So pi by a. So the value of this integration we found out to be pi by a, but if you see the original integration is different. It is x square plus a square and its whole square is present in the denominator. So what we will do? So now if you see, we know the integration and the derivative are interchangeable. So what we will do? Suppose we take derivative del by del a of this integration minus infinity to plus infinity dx by x square plus a square. So if we can written this as, we can write this as, suppose this is the part. So we can write this as minus infinity to plus infinity del by del x of 1 by x square plus a square, and after that there will be dx. So this part can be written like this. So we know the del by del x of del by del x of 1 by x square plus a square will be how much? Again, del by del x of 1 by x square plus a square will be minus 1 by x square plus a square whole square into 2a. So it will be minus 2a divided by x square plus a square whole square. So in that case, if you compare this with the integration value we obtained pi by a, so there is another minus 2a term is coming here. So if you put this term, then what will it give? It will give the integration of minus infinity to plus infinity dx divided by x square plus a square whole square will be pi by a into 1 by 2a. It is minus 2a again. If you take the integration of the right hand side, like pi by a, so this pi by a, there will be another integration. If you compare, if you take the integration del by del x of minus infinity to plus infinity dx by x square plus a square will be del by del x of pi by a. So it will be minus pi by a square. Now this part we obtained as minus infinity to plus infinity dx into minus 2a divided by x square plus a square whole square, which will be equals to minus pi by a square. So this minus 2 will be coming in that in the other side. So it will be minus infinity to plus infinity dx divided by x square plus a square whole square will be minus pi by a square into 1 by 2a. So this will be positive again because there is one negative sign in both right side and left side. It will be pi by 2a cube. So we needed the value of this integration. We needed the value of this integration. So the left hand side of the equation now became minus pi by a square into minus 1 by 2a. So it became pi by 2a cube. Now there was another term mod n square. So n square, sorry, the n square will not be here initially because so if you do this, it will be mod n square into the integration value is pi by 2a cube. It is equals to 1. Then n square mod will be 2a cube divided by pi. So n will be 2a cube divided by pi square root. So the value of the normalization factor is 2a cube by pi square root. So if you see, the correct option will be option A, which is 2a cube by pi. So basically what we did in this question, the question was the wave function is given and this is a normalized wave function. So if the wave function is normalized, we need to find out the value of n, and the range of x is also given, which is minus infinity to plus infinity. Now if you talk about the normalization condition is integration of minus infinity to plus infinity psi star psi dx equals to 1. So the integration value of 1 by x square plus a square, we know the integration value of 1 by x square plus a square, but here in the denominator there is x square. So first we will take the value of this integration, which we know it is 1 by a tan inverse x by a. So this value comes out to be pi by a. Now if you take derivative both the sides, then this term becomes x square plus a square whole square, and there is another term in the product which is minus 2a because we took the derivative. So now the derivative and integrations are interchangeable. So accordingly we will find the derivative will also be taken on the right hand side also. So the right hand side value will give minus pi by a square. So the additional minus 2a, if you take it to the right hand side, it will give you the desired value of the integration. And according to that value, we found the value of the integration is pi by 2a cube. Now n mod square into the value of the integration, that is 2 by pi by 2a cube is equals to 1. Then the value of n is 2a cube by pi and its square root. So this is the overall solution of this question. I hope this is clear to you. Then let's go to the next question. And again, the question says, find the probability that a particle can be found between x equals to 0.35 and 0.45 when the particle is limited to the axis and has wave function psi equals to ax for x between 0 to 1 and 0 for x less than 0 and x greater than 1. So the wave function is ax between 0 to 1. So the wave function has the value only between 0 to 1, and other and in other sides or in other values or in other ways the value of the wave function is 0 only. So first, what we will do now, the options are option A 0.028, option B 0.048, then option C 0.088, and option D 0.098. So these are the options. First, what we need to do, since you see here the wave function is given, but the wave function is not normalized. So first, we need to normalize the wave function. Then, after normalizing the wave function, we will calculate the probability. This type of problems we have already discussed in the previous class also. So I'll give you a few minutes to try this question. Then we will discuss. Let's solve this question. Now the question was the value of the wave function is given and we need to find out the probability of the particle between x equal to 0.35 to x equal to 0.45. Now, if you initially see the wave function is given is psi equals to ax when x varies from 0 to 1 and it is 0 other regions. So, if you roughly plot the nature of the wave function, now you clearly see it varies linearly with x and there is no other wave function. So if you plot the wave function, it will be somewhat like this. Then suddenly drops to 0. So this is x equal to 0 to x equals to 1. And this is right proportional to x, which is ax. So here the wave function is 0 and here the wave function is 0. But since here ax is given, the wave function is not normalized. And in order to find the probability of the particle, we need to normalize the wave function, because only when we can correctly find out the probability, because what the normalization does, the normalization makes the wave function acceptable. That is, after normalization, we found that the total probability of finding the particle in whole space is 1. So if you see, the wave function of the particle is between 0 to 1. So we will normalize the wave function in the limit 0 to 1, because otherwise the wave function value is 0 only. So we will normalize the wave function between 0 to 1. So according to this, the normalization condition will be integration 0 to 1 psi star psi dx equals to 1. So which will give integration 0 to 1. Psi star is again psi and psi star both are equal, because psi x the wave function is real. So then it will be ax into ax dx equals to 1. Then it will be a square integration of 0 to 1 x square dx equals to 1. Then a square into this is x cube by 3, 0 to 1 equals to 1. Then it will be a square into 1 by 3 minus 0 will give you 1. Then a square into 1 by 3 equals to 1. A square equals to 3. And a is root 3. So this will be the value of the normalized constant, that is a. So now if you write the wave function will be psi equals to root 3x when x is from 0 to 1 and it is 0 in other region. So now what we will do, we need to find out the probability. So for probability, what we will do, again we will integrate within the given limits, and the given limits are from 0.35 to 0.45. So the probability between 0.35 to 0.45, what will it be? It will be integration 0.35 to 0.45. Again, psi star psi dx. So what will be? It will be 0.35 to 0.45 root 3x into root 3x dx. Then it will be 3 will come out. Then it will be x square dx integration 0.35 into 0.45. This is 3 into x cube by 3, 0.35 to 0.45. So these 3 gets cancelled. So it will be simply 0.45 cube minus 0.35 cube. So what will be the value if we calculate 0.45 It is 0.091125. 0.091125 minus Q. It is 0.042875. So it will be minus 0.04875. So it is coming out to be 0.048. And if you see the options, the correct option will be option B, 0.048. So you see the or if you convert it to percentage, so it will be 4% only, or 4.8%. So you see the wave function, the wave function is such a way that the form of the wave function is such that the probability of finding the particle is only 4.8% between 0.35 to 0.45, because you see the nature of the wave function is increasing. So if you again calculate the probability of finding the, so basically if you see if the wave function is equiprobable in all the spaces, then between 0.35 to 0.45, it should have been 10%, because the change is only 0.1. But if you see the wave function is increasing linearly, so if you again try to calculate the probability between 0.65 to 0.775, it will be greater than 10%, because you see the wave function is increasing linearly. So the probability also will increase linearly, because the mod of the wave function gives us the probability of finding the particle. So so the correct option will be option B, which is 4.8%. So what we did in this question, so first we normalize the wave function, because only then we can calculate the correct probability, because the normalization constant or the normalization factor gives us the probability of finding the particle in the whole available space is 1. So if we normalize the wave function, the normalization constant, the value of the normalization constant, that is A, was found to be √3. So putting that value, we get the probability of finding the particle between 0.35 to 0.45 is 0.048, and the correct option is option B. Then let's go to the next question. The question says a particle is moving in a region x from 0 to L, and it is associated with the wave function psi of the form 2 by L root sin n pi x by L. Calculate the expectation value of the momentum of the particle. The options are option A 0, option B h cross, option C minus I h cross n pi by L, and option D n pi by L square. So like in previous interaction session, we have already discussed this type of problem where we needed to find out the expectation value of the position, but here it is given the expectation value of the momentum, and the wave function is given. And if you see the wave function is normalized. There is no normalization constant. The normalization constant would have been 2 by L root over, which is already present in the expression of the wave function. So we simply need to integrate the wave function in order to find out the expectation value of the momentum. So I will give you a few minutes to try this question, and after some time we will discuss. Let's solve this question. The question is the wave function is given and we need to find out the expectation value of the momentum. So if you see this wave function is the wave function is a particularly in a one-dimensional box, because if you see the form of the wave function is 2 by L root over sine n pi x by L. So in order to, since this wave function is normalized, we don't need to normalize the wave function. So you should always remember that whenever the question comes and there is wave function, you first need to check whether the wave function is normalized or not. So if you are not normalizing the wave function, then if you are calculating these expectation values and the probabilities, then all the calculations will be wrong, because since the wave function is not normalized, you are not considering that the total probability of finding the particle is 1. It will be less than 1 or greater than 1 corresponding to according to the normalization factor. So first you need to normalize the wave function, and after that you can solve for any value of the any expectation value of any quantity. So if you talk about the expectation value, so uh, in the last class we had discussed, suppose x, we want to find out the expectation value of this operator of the physical quantity x, then what will be the expectation value? It will be integration minus infinity to plus infinity psi star psi dx psi star x psi dx divided by integration minus infinity to plus infinity psi star psi dx. So this needs to be 1 since the wave function is normalized. So this is the condition of normalization. Then here in our case, it is given that we need to calculate the expectation value of the momentum, and we know the operator of the momentum in quantum mechanics is given by minus I h cross del by del x. So what we will do, we will, in order to find the expectation value momentum, we will take the integration, and since the particle is moving in a region 0 to L, so we will take the limit of the integration from 0 to L. So this is 0 and this is L. Then psi star, again the wave function is real, so both psi and psi star will be equal. So it will be 2 by L sine n pi x by L. Then there will be operator minus I h cross del by del x sine n pi x by L dx. Now you see, since the operator contains the derivative with respect to x, we can't directly multiply the two wave function and write sine square n pi x by L. So we will first write one wave function, that this is psi star and this is psi and this is the momentum operator. So if you take the derivative, then it will be so cos n pi x by L into n pi by L. So the expectation value of momentum will be, so 2 by L will be coming outside. There will be integration 0 to L, 2 by L into minus I h cross also we can take outside. So it will be sine n pi x by L into the derivative of sine n pi x by L, which will be cos n pi x by L into n pi by L dx. So if you take all the constants outside of the integration, then it will be minus I h cross n pi by L square, then integration 0 to L. You see this is 2, if you take inside, it will be 2 sine n pi x by L into cos n pi x by L dx. Now this value 2 sine x into cos x is nothing but sine 2x. So it will be minus I h cross n pi divided by L square, 0 to L, the limits of integration, it will be sine 2 n pi x by L dx. And if you integrate it, the integration value for sine, the integration becomes 0. because sine 0 is 0 and sine L if you put here it will be sine n pi and sine n pi is again 0. So this integration will be 0. Then the value of the I s cross n pi by L square into 0 and the answer will be 0. So the average momentum or the expectation value of the momentum of the particle in a one-dimensional box is 0. So how it is being possible to 0? Because if you see this wave function is if you see the nature of the wave function, there are two components. One is along positive x direction, another along negative x direction. So for half part of the wave function, that is 0 to x pi, if you calculate there will be negative value of momentum and there will be positive value of momentum, then both these momentums gets cancelled and you find out the expectation value momentum is 0. Or also we can say that since the expectation value of the momentum is 0, the particle can't go outside this box because the wave function or the potential outside this box is infinite. So also particle can't move away from this well. So this is also called as one-dimensional potential wave, infinite potential wave. And the correct option will be option A. So this question was to find out the expectation value of momentum of the particle and the wave function was given. And the form of the wave function is a particle in a one-dimensional box. So since the wave function is normalized, if we consider the expression of finding the expectation value of any quantity, so the denominator becomes 1 and the numerator, if you calculate the integration, you will simply we need to do the integration, and if you do the integration, the value you will get is 0. So the expectation value of momentum of a particle in one dimensional box is 0. And also you can see this expectation value is 0 for any value of n. So since we have taken here the wave function is n pi x by L, so this is a generalized wave function. So if you put any value of n, that is n equal to 1, 2, 3 up to any value in every state or every, so this n equal to 1 means ground state, then n equal to 2 means fast accelerator, like that. So in any state, the total or the average value of the momentum will be 0 for the particle. Okay, so then go to the next question. The question says an electron is confined in a cubical box, each side being 1 angstrom. Calculate the energy of the electron in the fast excited state. The Planck's constant is given. The Planck's constant value is H equals to 6.626 into 10 to the power minus 24 joule into second. The options are option A 113 electron volt, option B 225 electron volt, option C is 425 electron volt, and option D is 625 electron volt. So we need to, what we need to find? We need to find out the energy of the electron in the fast excited state. So this is the fast excited state. So we just discussed. Now this is in confined in a cubical box, each of side. So this is a three-dimensional well potential is given. And if you see the Planck's constant, the constant is given and the unit is joule into second. So the energy you will be calculating, the unit of the energy will be joule. So since the options are given in electron volt, so after calculating the value, we need to convert the energy into electron volt, and you know the conversion factors. So I'll give you a few minutes to try this question. Then for some, then after some time we will discuss about the question. So the question is, the electron is confined in a cubical box, each side being 1 angstrom. So if you see the it is a one-dimensional box potential. We take the x is varying from 0 to L. So here the value of L is 1 angstrom, which is 1 into 10 to the power minus 10 meter, and the value of Planck's constant is given, which is 6.626 into 10 to the power minus 34 joule into second. Now, if you talk about particle in one-dimensional box, the energy value is given by n square h cross square by 2m a square, where a is nothing but this L. So if you put the question here is given in a cubical box. So here we will put the formula for three-dimensional box. So this n square, this is in 1D, but in three-dimensional case, the n square gets converted to nx square plus ny square plus nz square, then h cross square divided by 2m a square. Now, if you see here, these nx, ny, and nz, if the now the length of the box is given, the box is basically a cube, and each side is of length 1 angstrom. So here the three sides, or the sides in three dimensions, both are equal, or all the sides are equal. So we are taking nx square, ny square, and nz square together. So we will simply put the value of a here as 1 angstrom. So if you put the value, then what will be the value? Now the question says what will be the energy of the fast excited state. So if you talk about the values of nx, ny, and nz, we know for one-dimensional potential, what happens? For one-dimensional potential, n varies from 1, 2, 3, like this. But since it is a three-dimensional case, so the values of nx, ny, and nz will vary from 1, 2, 3, 4, like this. It will be varying from 1, 2, 3, 4. It will be varying from 1, 2, 3, 4, 5 up to infinity. So for ground state here, n equals to 1 for ground state and n equal to 2 for excited state, fast excited state, n equal to 2. But if you see here, for three-dimensional case, the ground state will be nx equals to 1, ny equals to 1, nz equals to 1. And if you consider about the fast excited state, so only one of the values of nx, ny, and nz will be 2. So for fast excited state, we can write nx equals to 2, ny equals to 1, nz equals to 1. Again, the value of ny can be 2 also. So the second type of state will be nx equals to 1, ny equals to 2, and nz equals to 1. And the third combination of nx, ny, nz will be nx equals to 1, ny equals to 1, and nz equals to 2. So if you see in all these three cases, the value of nx square plus ny square plus nz square will be same. So it will be what? It will be 1 square plus 1 square plus 2 square. It will be 4 plus 1 plus 1, which will be 6. So if you see here, nx, ny, nz are different. So since nx, ny, nz are different in these three cases, the wave function of the particle will be different in three cases, but the energy will be remaining the same. Now this condition is called as degeneracy. And here, for fast excited state of three-dimensional box, we are getting the degeneracy as 3. So here, the degeneracy is 3. That is, there are 3 different states which have different wave function, but the energies are same. So here, what do we need to calculate? Here, we need to calculate the energy of the electron in fast excited state. So what will be the formula for fast excited state? So E fast excited state will be 1 square plus 1 square plus 2 square. This is nx square plus ny square plus nz square. then pi square h cross square divided by 2m. In a square, we will put 1 into 10 to the power minus 10 square. This is 6 into pi square. If you see, if you convert h cross square into h, so h cross is h by 2 pi. So this pi will get cancelled with both denominator and numerator. Then there will be 8m square in the denominator. So it will be 6h square divided by 8m 1 into 10 to the power minus 10 square. So now what will be the value of m? The value of m will be mass of electron. So mass of electron is 9.1 into 10 to the power minus 31 kg. The value of H is also given 6.627 into 10 to the power minus 34 joule into second. And value of A is, or the value of L is 1 Armstrong, which is 1 into 10 to the power minus 10 meter. So if you put these values, so it will be how much? It will be 6 into 6.627 into 10 to the power minus 34 square divided by 8 into 9.1 into 10 to the power minus 31 into 1 into 10 to the power minus 20. So if you calculate it, what you will get? It will be around 3.6 into 10 to the power minus 17 joule. And we know 1 electron volt is 1.6 into 10 to the power minus 19 joule. So 1 joule will be 1 by 1.6 into 10 to the power 19 electron volt. So if you put these values, then if you convert it, what you will get? You will get the energy value in terms of electron volt is 225 electron volt. The correct option will be option B, which is 225 electron volt. So when the electron is confined in a cubical box of each side having length 1 Armstrong, the energy of the electron in the fast excited state will be how much? It will be 225 electron volt. Now this is the energy of fast excited state. Now if we talk about the ground state, then for ground state the value of nx, ny and nz both are all are 1. It will be 1 square plus 1 square plus 1 square, so it will be 3. So here it is 6 into h square. In the ground state the expression will be 3 into h square divided by the denominator will be same. So if you see the value of the ground state energy will be half of this value. So it will be 112.5 electron volt. So now see, in atom we know in case of hydrogen atom, the ground state energy of electron in the hydrogen atom is only 13.6 electron volt. So if you can clearly see, if the form of the potential is different, the energy value is also changing. We know the in case of hydrogen, we consider the potential to be a coulombic potential, which is varying 1 by r with respect to r. So here you can clearly see when the form of the potential varies. So the electron inside the atom is not experiencing the potential which is explained in this question, that is potential in one dimensional box. So the electron is being subjected to a different type of potential, and that's why the energies of the electron are different. So the form of the potential determines what will be the energy of the particle which will be present in that potential. So this was the fourth question. Now the fifth question says, find the position of maxima of the radial wave equation of the radial wave function R21 of the hydrogen atom, and R21 wave function is given. It is 1 by root 24 A0 to the power minus 5 by 2, then R into exponential minus R by 2A0, and the A0 value is given. It is 0.53 Armstrong. Now the options are 0.53 Armstrong, B 1.06 Armstrong, 1.59 angstrom and then 2.12 angstrom. So this type of question we had already discussed in the previous session. Since it is given as the position of maxima, we know if you simply take the derivative with respect to A, then it will give us the radial position at which the, if you take the derivative with respect to R, because here R is varying, so it will give us the value of the point where the wave function has its maximum value, or that or otherwise we call it as maxima. So if you take the integration, or the correct answer can be found out by taking the derivative of this wave function with respect to radius r. So it will be d by dr of r21 equals to 0, which implies d by dr of r21 is 1 by root 24 into a0 to the power minus 5 by 2 r e to the power minus r by 2a0 equals to 0. Then if you take the derivative, then first term it will be 1 by root 24 a0 to the power minus 5 by 2, it will be common. Then in one case it will be e to the power minus r by 2a0 plus r e to the power minus r by 2a0 into minus 1 by 2a0 will be 0. So if you see, if you take e to the power 1 by root 24 a0 to the power minus 5 by 2 into exponential minus r by 2a0, then 1 by root 24 a0 to the power minus 5 by 2 exponential minus r by 2a0. Then the remaining term will be 1 minus r by 2a0 equals to 0. Now this term is 0. This term can't be 0. So this term will be 0. So it is 1 by r by 2a0 equals to 0. Also, if you see here it is also r present. So now exponential, again this e to the power minus r by 2a0 will be equal to 0. So these are the two possible equations, or these are two possible solutions. Now if you talk about e to the power minus r by 2a0 equals to 0, then r by 2a0 will be infinity, or r will be infinity. But this is not acceptable, because according to the feasibility of the wave function, in order to be acceptable wave function, the value of the wave function is 0 at r equal to infinity. So the value of r equals to infinity is not acceptable for this case. So the wave function should be 0 at infinity, and the max, because, and in this question we need to find out the maximum of the wave function. So this option is not acceptable. Then the remaining option is 1 by r divided by 2a0 equals to 0. Then 1 equals to r by 2a0, which gives us r equals to 2a0. So again, the value of a0 as given in the question, it is 0.53 angstrom. It will be 2 into 0.53 angstrom, which is 1.06 angstrom. This is the correct option. The question was find out the position of the maximum of the radial wave function. The radial wave function is also given. So now in order to find the maximum of the radial wave function, we need to take the derivative with respect to r, because r is the variable in this wave function. This is the radial part of the wave function. So r21 value is given. So if you take the derivative, the two possible solutions will be exponential minus r by 2a0 is 0 and 1 minus r by 2a0 is 0. But the exponential part, if you equate it to 0, then r will be infinity only. But if you calculate the remaining part, that is 1 minus r by 2a0, the value is coming out to be r equal to 2a0. And if you consider two values, r equals infinity is not possible or not acceptable, because the wave function reduces to 0 at infinity. So the correct option will be option option B, which is 1.06 angstrom, that is 2a0. So the maxima position of the radial wave function is 2a0. I hope this is clear to you. Then let's go to the sixth question. The question says, find out the expectation value of energy of the ground state of hydrogen atom. The ground state of hydrogen atom associated with the normalized eigenvalue wave function is psi equals to 100, psi 100 equals to 1 by pi a0 q e to the power minus r by a0. So these are the options. Option A minus 1.36 electron volt, 3.4 electron volt, 1.08 electron volt, and minus 7.48 electron. Actually, the option A is not written correctly here. It will be 13.6 electron volt. It will be 13.6 electron volt minus 13.6 electron volt. This is the correct. This is the this is written correctly. This is the wrong. Then the option B is minus 3.4 electron volt to 1.08 electron volt and minus 7.48 electron volt. So we need to find out the uh, energy of the ground state of hydrogen atom. I will give you a few minutes to try this question. Then after some time we will discuss about it. If you see this question, the question says what will be the expectation value of the energy of the ground state of a hydrogen atom, and we know the wave function is also given, and the wave function is again normalized eigenvalue wave function, and we know that the energy of the ground state of a hydrogen atom is nothing but the minus 13.6 electron volt. So the correct option will be option A, which will minus 13.6 electron volt. Then question number 7. The first line in the rotation spectrum of carbon monoxide is 3.8424 centimeter inverse. Find the bond length of carbon monoxide molecule. Reduced mass of carbon molecule is given. It is 1.14 into 10 to the power minus 26 kg. The options are option A 1.13 Armstrong, option B 2.26 Armstrong, option C 3.39 Armstrong, and option D 4.52 Armstrong. So we need to find out the bond length of carbon monoxide molecule, and that is the distance of separation between carbon and oxygen. The reduced mass of the molecule is given, and the first line of the rotation spectrum is given. Now, if you talk about the rotational spectrum, the rotation energy is given by Ej equals to J square by 2I, where I is the moment of inertia, and according to quantum mechanics, we know J square is given by J into J plus 1 H square, or H cross J into J plus 1 H cross square. So the value will be H cross square divided by 2I J into J plus 1. Now, if you talk about the since the first line of the rotational spectrum, which is given in terms of centimeter inverse, so in order to convert energy into centimeter inverse, we will divide it by Hc, because E is equals to Hc by lambda. So 1 by lambda will be E by Hc. So E J by Hc will be H cross square divided by 2I Hc J into J plus 1. It will be H square divided by 8 pi square I will be H by 8 pi square IC J into J plus 1. So if you see the H will get cancelled from the numerator and denominator, so there will be only single H. It will be H by 8 pi square IC J into J plus 1. So this is the, we can take it as Fj. So if you see, if you the value, if you consider the value of J, the value of J is J equals to 0, 1, 2, 3, like this. So for J equal to 0, now this constant is called as B. If you write this constant as B, then for J equal to 0, this Fj will be 0. For J equals to 1, Fj will be your 1 into 1 plus 1, that is 1 into 2 is equal to 2, so 2B. Then for J equal to 2, F2 will be 2 into 3, 6B. Then J equal to 3, F3, 3 into 4, because 3 into 3 plus 1, 3 into 4, 12B. So like this. So now if you draw the energy levels, so it will be 0, then 2B, then 6B, then 12B, like this. So if you see, the spacing is here 2B, that is 2B minus 0. Here the spacing is 4B, and here the spacing is 6B. So the energy levels are not equally spaced. And here, if you see, the question is the first line of rotation spectrum of carbon monoxide is 3.8424 centimeter inverse. So according to the selection rules, for transition delta J will be plus minus 1. So here the first transition, this is J equal to 0, J equal to 1, J equal to 2, J equal to 3. So the first transition will be from 1 to 0. So the change in energy is 2B minus 0 is equal to 2B. So Fj, delta Fj is 2b minus 0, which is 2b. Now this 2b is given. 2b is 3.8424 centimeter inverse. So 2b is 3.8424 centimeter inverse. B is 1.9212 centimeter inverse. So the value of B is, again we know it is h by 8 pi square IC. So h by 8 pi square IC equals to 1.9212. That implies we need to find out the value of I again. If you see, we already know I is the moment of inertia. That moment of inertia is given by mu r square, where mu is the reduced mass and r is the separation, that is nothing but the bond length. So the value of I will be, from this question, value of I will be h by 8 pi square BC. I will be h by 8 pi square B into C. So h value we know 6.626 into 10 to the power minus 34 divided by 8 into pi square into B is 1.1 is 1.9212. But if you see here, the value of h we have taken in terms of joule into second. So here we have to take the value in meter inverse. So if you convert centimeter inverse to meter inverse, it will be 100 multiplied here. So it will be 192.12. It was 1.9212. So it will be multiplied by 100. It will be 192.12 into C. C is 3 into 10 to the power 8 meter per second. So if you calculate all this, it will give you 1.456 into 10 to the power minus 46 kg into meter square. Now this value is mu into r square, mu co into rco square. So r will be 1.456 into 10 to the power minus 46 divided by the value of mu is given. It is 1.14 into 10 to the power minus 26. It is 1.14 into 10 to the power minus 26 square root, and this value, if you calculate, it will give you 1.13 into 10 to the power minus 10 meter, which will be 1.13 Armstrong. So the correct option will be option A, that is 1.13 Armstrong. So here the question was, the first line of rotational spectrum of carbon monoxide is 3.8424 centimeter inverse. So the bond length we need to find out, and the reduced mass of carbon monoxide molecule is given. Now if you talk about the energy levels of rotational spectrum, then the energy levels are given by J square by 2I, where I is the moment of inertia, and we know the moment of inertia nothing but mass into the square of the distance between the two particles. So here one is carbon atom, and another is oxygen atom, and they are bonded at some distance, and that distance we need to find out. That is the bond length here in this case. So if you calculate, then the energy expression can be written as h cross square divided by 2I j into j plus 1. So we put, since the first line is given in terms of centimeter inverse, so in order to convert energy to centimeter inverse, we will divide energy by hc. So we know E is equals to hc by lambda. So 1 by lambda will be E by hc. So 1 by lambda, the unit of 1 by lambda is centimeter inverse, that is the wave number unit. So if you put the values, then the expression will be coming out to be j into j plus 1 h by 8 pi c, and this constant we can collectively called as B. So for different values of there will be different energy levels, and if you see the energy levels, they are not equally spaced, and the first member of the first line will be corresponding to the transition between j equal to 0, j equal to 1 to j equal to 0, because the selection rule given here is delta is equal to plus minus 1. So according to the selection rule, 2b will be the first line, the the value of the first line will 2b is to value of 2b is given to be 3.8424. So from this b can be calculated, and if you put the value of b here, then the moment of inertia value will be calculated, and from this moment of inertia value, if you divide the moment of inertia by the reduced mass and take the root over of it, then it will give you the bond length, and here in this question the bond length was found to be 1.13 angstrom. I hope this is clear to you. Now let's go to the next question. The question says the absorption spectrum of HCl molecule consists of 3 consecutive lines with the wave number 83.03, 103.73 and 124.30 centimeter respectively. What J value do they correspond? So if you see, there are 3 consecutive lines with wave number 83.03, 103.73 and 124.30, and all these lines are in terms of wave number unit, that is centimeter inverse. Now we need to find out what will be the corresponding value of J. The transition is being occurring. So since there are 2 values, then there are 3 J values. So since there are 3 values of the lines, we will be getting 3 J values, and we need to find out these 3 J values. Options are option A 4, 5, 6, option B 3, 4, 5, option C 5, 6, 7, or option D 7, 8, 9. So we will find 3 consecutive J values. So what will be the 3 consecutive J values? I will give you a few minutes to try this question, then I will discuss. So now there are 3 values. So we just talked about the transitions occurring in the rotational spectrum. So in rotational spectrum, these are the 4 levels. Now let's talk in a generalized way. Suppose there are, here we need to find out the value of J. Suppose there are different levels, and we will take that. The generalized, we will generally take the value of J to be simply J, that is small j. So there are different levels and there are different transitions. Now suppose there are 2 J values, one is J and another is J plus 1. Now suppose the transition occurs from, this is J plus 1 and this is J. Now the transition occurs from J plus 1 to J. Now for this J level, the energy will be what? It will be B J into J plus 1. And for this J level, the energy will be B J plus 1 into J plus 2. Is not it? Because here the value of J is J, but here it is J plus 1. So in case of J, we put here J plus 1, then J plus 1 means J plus 1 plus 1, that is J plus 2. So these are the 2 values. Now the transition, when the transition is occurring, then it will be B J plus 1 into J plus 2 minus B into J plus 1 into J. So if you take B J plus 1 common, it will be J plus 2 minus J. J gets cancelled out. It will be 2B J plus 1. So this is 2B J plus 1. So if the transition occurs from J plus 1 to J, that is 2B J plus 1. So similarly, if the transition will occur from J plus 2 to J plus 1, then what will be the value of delta F? Delta F will be 2B it is, you see here there are two values, j and j plus 1. The higher value is being reflected in the expression. So here the higher value will be again reflected. It will be 2b j plus 2. Similarly, if the transition occurs from j plus 2 to j plus 3, then the value of the delta f will be 2b into j plus 3. Now, so if you compare this concept, then the given values of 83.03, 103.73 and 124.30, it will give us 2b into j1 plus 1 equals to 83.03, then 2b into j2 plus 1 will give us 103.73, then 2b into j3 plus 1 will give you 124.30. Now this can be written as, suppose this is, we'll take j1 equal to j, then it will be j plus 1, this will be so this will be 2b into j plus 1, 2b into j plus 2, 2b into j plus 3. Now if you equate the first equation, now this is equation 1, this is 2, and this is 3. Now if you equate the first equation, then 2b j plus 1 equals to 83.03. So 2j plus 1 will be 83.03 by b. Now, in the question, this value is given as 80 to be so we have to use the two equations, then we can get the value of b. So here if you see, in order to find the value of j, we need to find the value of b. We don't know the value of b, so in order to get the value of b, we will use these two equations. So now if you see if you subtract equation 2 minus equation 1, then it will give us 2b j plus 2 minus 2b j plus 1 will give you 2b j plus 2 minus j minus 1. It will be 2b, which is will be equal to 103.73 minus 83.03. This value is how much? It is 20.7 centimeter inverse. So 2b is 20.7 centimeter inverse. So b will be 20.7 divided by 2, which is 10.35 centimeter inverse. Now the value of b is given. So from this equation, suppose this is equation 4. From this equation, from equation 4, 2 into j plus 1 is 83.03 divided by b. So 2j plus 1 equals to 83.03 divided by 10.35. Or you can write j plus 1 equal to 83.03 divided by 20.70. Now, if you divide 83.03 by 20.70, the value is coming out to be 83.73 divided by 20.70. The value is coming out to be 4.04. So we can simply take it as approximate to be, this is 4.04. So approximately we can take it as 4. So since j plus 1 is 4, j will be 4 minus 1, which will be 3. So 1 is 3. Then the other three values are j plus 2, j plus 3. So one value will be j, this is j1 is 3, j2 will be j1 plus 1, which will be 4, j3 will be j2 plus 1, which will be 5. So the j values are 3, 4 and 5. So the correct option is option B, 3, 4, 5. So here we had the three lines. So we know if the transition occurs between two levels, the general expression for the value of the spectral line is 2b into j plus 1. Now this 2b into j plus 1 is 83.03. Then if the transition occurs from next transition, the next transition corresponds to j plus 2 to j plus 1, and it will be similarly 2b into j plus 2. So like this, there are three equations, and from these three equations, we need to find out the value of j. But to find out the value of j, we need the value of b. So for value of b, we will find that if the transition is occurring, we will subtract equation 1 from equation 2. Then we will get the value of b, and from that value of b, if you put it in the equation 4, we will get the value of j. Since one value of j is known, we can add 1 to it, we can get the higher value of j. So the three values are 3, 4, and 5. So the correct option is option B. Then question 9. Rotational constant of HCl molecule So the rotational constant of HCl molecule is given, which is 1035 meter inverse. Calculate the intermolecular separation of HCl molecule, where reduced mass of HCl molecule is 35 by 36 into mass of proton, and mass of proton is given. Option A is 1.15 Armstrong, option B is 1.29 Armstrong, option C is 1.47 Armstrong, and option D is 1.67 Armstrong. Now, if you see here, we know the value of B is So we know the value of B. The value of B is nothing but H by 8 pi square IC, is not it? So see here, the rotational constant of HCl molecule is given. Now the rotational constant is known as B. So this B is nothing but the rotational constant, and the expression of B is H by 8 pi square IC. So I will be H by 8 pi square BC. Then if you put the values, it will be 6.627 into 10 to the power minus 34. Since here, if you see the value is given in terms of meter inverse, we can use the conventional values like H is 10 to the minus 34 joule into second, then 8 into pi square into B is 1035, and C is 3 into 10 to the power 8. So if you calculate the value, it will be coming out to be 2.7 into 10 to the power minus 47 kg into meter square. Now, the reduced mass of HCl molecule is given, and we know the reduced mass is nothing but M1 M2 divided by M1 plus M2. So we know for HCl, one is hydrogen, another is chlorine. So for hydrogen, there is only one proton, and for chlorine, there are 35 proton, or 35 proton plus neutron. So we will consider proton and neutron mass to be equal, and we will take it as mass of proton. So it will be mass of proton into 35 mass of proton divided by mass of proton plus 35 mass of proton. And this value is 35 MP divided by 36. This is 35 MP square divided by 36 MP. It will be 35 by 36 mass of proton. So this value is given here. So if you put these values, you can easily calculate the intermolecular separation of HCl. So I is nothing but mu r square And this value of I we found out to be 2.7 10 to the power minus 47. 2.7 into 10 to the power minus 47 kg into meter square. Then R will be how much? 2.7 into 10 to the power minus 47 divided by mu. Then mu is 35 by 36 into mass of proton. Mass of proton is 1.67 into 10 to the power minus 27. This will be 1.624 into 10 to the power minus 27 kg. So it will be 2, this will be root over of it. It will be 2.7 into 10 to the power minus 47 divided by 1.624 into 10 to the power minus 27. This value will be how much? It will be 1.289 into 10 to the power minus 10 meter, or we can be equated it to 1.29 Armstrong. So if you see the options, the option B is again correct. So the correct option is option B, that is 1.29 Armstrong. So here the rotational constant of the molecule is given. So from that rotational constant, we calculated the value of moment of inertia. And since the moment of inertia nothing but mass into the intermolecular separation square, using that value of moment of inertia, we calculated the internuclear separation of hydrogen chloride or hydrochloric acid. And how the reduced mass is calculated, I also showed here. This reduced mass is nothing but m1 m2 divided by m1 plus m2. We put the value of mass of hydrogen is nothing but 1 proton, and the mass of chlorine is, we know the atomic number of chlorine is 17 and the mass is 35.5. So if you put it to 35 and take the mass of proton and mass of neutron to be equal, then the mass will be 35 into mass of proton. So from this, we got the value of intermolecular separation is 1.289 10 to the power minus 10 meter, or 1.29 Armstrong. Now, if you see in hydrogen chloride, the hydrogen plus and Cl minus, there are, so the bond length is nothing but 1.29 Armstrong. Is the answer. So I hope it is clear to all of you. Then go to the next question, which is the last question of today's session. The question says, again the same type of question, the bond length of nitrogen oxide is 1.15 Armstrong. Find out the moment of inertia of nitrogen oxide molecule. Consider the mass of proton is 1.67 10 to the minus 27 kg, and reduce mass of nitrogen oxide is 224 by 30 into mass of proton. The options are 1.65 into 10 to the minus 46. Option B is 2.37 into 10 to the minus 46, 4.17 into 10 to the minus 46, and 5.27 into 10 to the minus 46 kg meter square. So now, if you see in previous question, the moment of inertia we first calculated and then we calculated the bond length, but here the bond length is given and we need to find out the moment of inertia. So it is very simple question. We don't need the rotational constant value also here. So if you see the moment of inertia is given as I is equals to mu r square, where mu is the reduced mass and r is the internuclear separation, that is the bond length. So I will be mu into 1.15 Armstrong, and the mu is also given. Mu is 224 divided by 30 into mass of proton 1.67 into 10 to the power minus 27 into, it is 1.15 10 to the power minus 10. So if you calculate it, you can easily get the value of moment of inertia is 1.649 into 10 to the power minus 46 kg into, this will be mu into square 1.4 kg into meter square, or it can be approximated as 1.65 to 10 to the power minus 46 kg into meter square. So the correct option is again option A. So this was a relatively simpler question in comparison to the previous question. So simply here we needed to find out the moment of inertia where the mass of the reduced mass of the molecule is given and the bond length is given, and simply we know the expression for moment of inertia is I equals to mu r square. So if you put the value of mu and put the value of r square, so r is nothing but the bond length and mu is the reduced mass. So all these values are given, so you need to simply put the values and calculate what will be the correct answer, and the correct answer we found it to be 1.65 × 10⁻46 kg. So with this question I come to the end of today's interaction session. So in the previous interaction, we solved a few problems which were related to quantum mechanics, and then today we solved initial few problems which were related to the wave functions and the finding out the normalization constant and different expectation values and different energies of the particular wave function in certain potential scenarios, different potentials. And towards the end, we solved a few problems related to the rotational spectra of the molecular spectra section. So in the next session, we will be discussing about a few problems. We will be based on again rotational and vibrational spectra of molecular spectra. So till then, I wish you good luck. That's it for today. That's it from my side.